Hello again. 3, 2, 1, 0. I'd like to talk about how computers communicate. And really what this is about data and how data is represented. Not so much about how the wires work and the connectors and so forth, but the actual data. Data is a representation of some kind of a value, of some kind of information. And if that information is coming from outside the computer, for example, right now I'm recording sound with my microphone. Sound is what we call analog information in that it can be represented as a value that is converted to a voltage. The microphone actually converts sound, which are wave pressures in air, into voltages which change with time. And those voltages then are converted then to numbers by the computer. But here's an example of an analog value, a light bulb. A light bulb can be all the way off or all the way on, but it can also be part way on. It can be dimmed, right? We can have a very dim light that's maybe 1/3 of the way on, or a brighter light that's 2/3 of the way on, or we can have it all the way on. So analog means that you can have anything from all the way off to all the way on, and anything in between. And a lot of things in the world are like that, right? They have lots of different possible values. Computers, though, don't work with analog values directly. Computers only deal with zeros and ones, or ons and offs. Digital, we call them digital numbers. In other words, numbers. And in its most basic form, digital is represented by ons and offs, zeros and ones. In fact, everything in your computer is represented by zeros and ones, ons and offs. And that could be similar to a light bulb. A light bulb could be all the way off with a switch or all the way on with a switch. Now, single individual zeros and ones are useful for some things, but many times we need to represent more than just a single on or off value, but we need to represent values in between like we do with analog. And so we do that by converting voltage levels, which is typically what comes into a computer from things like microphones and other analog devices, or joystick, for example, uses analog values that get converted into numbers. A camera converts analog values of light levels into numbers. And so those are, in some part of the equipment, that's represented as voltages, because stuff gets converted to electrical signals and then gets converted to numbers. And then we use number systems to represent those numbers. And numbers are represented in a computer as more than one binary or on-off value. And then other things are represented by symbolic codes. For the numbers, we use the binary number system. That's a series of ons and offs, or zeros and ones. And many times, because binary numbers are hard to use for people to deal with, we use hexadecimal numbers to represent those numbers. And then for text type information, like a word processor uses, we will use a code called ASCII, American Standard Code for Information Interchange. Let's talk a little bit about binary numbers. Binary numbers are numbers made up of just zeros and ones. Now, our everyday numbers that we use are decimal numbers. They are represented by the numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And so we have a total of 10 possible digits to use to represent our numbers. In binary, you only have 2. You only have 0 or 1. So, for example here, how would we represent a number in binary? Well, what we do is we set up places. We have in decimal, we have the ones place, the tens place, the hundreds place, the thousands place, the 10,000s, and so forth. Well, we do the same thing in binary, except instead of being based on the number 10, it's based on the number 2. It goes up because we have 2 digits. We have 0 or 1. So we have the 1's place, the 2's place, the 4's place, the 8's place, the 16, the 32, 64, and the 128 place. So let's suppose we wanted to convert a number that was in decimal to binary. How would we do that? Well, what we would do is we would start on the left side of our byte. Now, this is called a byte. This is 8 bits here, total of 8 bits. A byte can hold a number between 0 and 255. So the number we want to put into our byte here is 114, so that'll fit. So what we do is we look at our number and we look at the most significant, or the largest place, most significant bit is the 7th, what they call bit 7, which is actually the 8th bit. And bit 7 is the 128, represents 128. If it's on, or 1, then that would be 128. Well, 114 is not as big as 128, so we put a 0 underneath it. Now I'm going to get my calculator out here, and so what I'm going to do is I'm going to put the number 114 into my calculator, and now I go to the next place over, and that's 64. Well, 64 is smaller than 114, so we can subtract that. So we'll go ahead and put a 1 underneath that, as we did here, and we would subtract 64 from that, and that gives us 50. Alright, and then we go to the next place, and we see that 50 is also larger than that place, which is the 32's place. So I would subtract 32 from that, and that would give me 18. So I go over to the next place here, and I see that 18 is larger than that place, which is 16. So I put a 1 under that, and I'd subtract 16 from what I have left, and that gives me 2. Then we go over here and we have 8. Well, 8 is too big. It's bigger than 2, so we put a 0 under it. 4 is too big, so we put a 0 under it. Okay, then we have the 2's place. Well, the 2 fits into 2, of course, and it fits in exactly 1 time, so we end up with 0 left over, and we don't have a room to put our 1 in, so we put a 0 under there. So you see, it's actually a converting from binary, a decimal number into binary is really a process of subtracting. And you subtract from the most significant digit of the number place, which would be, in the case of a byte, would be the 128th place, going all the way down to the 1's place until you end up with 0. And any number between 0 and 255 could be converted that way to fit into an 8-bit binary number, or a byte. If you have a bigger number than that, then you'd have to use a bigger number of binary digits to hold it, and that would be a larger, what they call, word. Now, binary is kind of clumsy to use. You notice that here we have this number 01110010. That's kind of hard to say. It would be nice to have a little shortcut for that, and so what we do is we use a shortcut code called hexadecimal, and here is a chart showing the hexadecimal codes. Now, hexadecimal represents the numbers 0 through 15 as its digits. In other words, hexadecimal means base 16, so it has 16 digits. The digits are 0 through F. Now it goes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. Each one of those represents 4 bits. You see those 4 bits here. Now there's 5 bits shown in this table because I want to show what happens when you go above that. But here you see 4 bits. So as we go across, we start at 0000, that's 0, 0001, that's 1, and then 0010, that's 2, 0011, that's 3, and it keeps going. And it goes through all the possible combinations of 4 bits, which goes all the way to 1111, and that's F. So you see, we can represent those binary numbers as a combination of 4 bits. Well, if we go beyond that, then we'd have to go to another binary place, which would give us, we'd have to use another hexadecimal number to represent that. And so this number here, which is actually the number 16 in decimal, represented as 1000, is 10 hex. Well, some people would say 10 hex, but it's really not proper to say that because it's not 10, it's 10 hex. And that was really 16. And then if we went another one, that would be 10001. You notice it's starting to repeat the pattern up here with these 4 bits, you see? See, it repeats the pattern. And so we'd keep doing that. And then we'd have to add another binary digit. We'd have to have more hexadecimal digits as well. Now, hex is a great numbering system for numbers that computers use because computers tend to use 8-bit chunks of numbers, 16-bit, 32, or 64-bit chunks, and 4 bits fits nicely even into that. So hex is an excellent way to represent binary numbers of those sizes. So here's a little chart showing all the hex numbers that we usually use, and this is hexadecimal 1 is decimal 1. Hexadecimal 2 is 2, and notice it's the same until you get to 9 here, but when you get to 10 decimal, then we call that A, and then 11 is B, 12 is C, D is 13, E is 14, F is 15, and that's how you convert between hex and decimal. When you get past 15, then we get to 10 hex, which is actually 16 decimal, 11 is 17, and so forth. So it works in 4-bit chunks, and you can easily convert the two. If you want to convert a hexadecimal number to decimal, what you do is you go in, this time in powers of 16. In other words, you have the 1's place, the 16's place, the 256, and the 4096 place, and so forth. Each one of these places goes up by 16 times. So 20 would be 2 16s and 0 1s, which would be 32. And here we have A4 hexadecimal. Well, A, that's, if you look that up on the chart, that's 10. So that would be 10 times 16, or 160. And then 1, if we have 4 under the 1's place, so that would be 4 added to the 160, giving you 164. Now, a lot of calculators have hexadecimal functions built into them, like this calculator here. I can switch it over to programming mode, and it has all kinds of good stuff in there. So, like I could type in a number here, like I've got the number A4. So if I put this calculator in hex mode, and I type in A4, and then if I click decimal, it'll convert it to there. There's our number, 164. Or I could convert it to binary, And there's another one called octal. We don't use that much anymore, but the octal was a base 8 system, which is 3 bits at a time. But that doesn't fit so nice and even in our usual computer word sizes. Another kind of code that's often used with binary is called ASCII. ASCII means it's American Standard Code for Information Interchange, and it just represents all the characters on your keyboard and some other characters too, punctuation marks and special characters. So ASCII is actually a pretty large number of different characters. There's 128 characters in the usual ASCII code set, and those are all the letters and numbers, both upper and lowercase letters, and all the punctuation things that you find on your keyboard. And these things over here, these are called control codes, and they're just different. Some of those are on your keyboard too, like carriage return is that's code 0D hex, you see there, and space bar, that's 20 hex. That's how you read this thing here. The letter A would be 41 hex. So that's how you convert between ASCII and hexadecimal and or binary. You can do that as well. And those represent all our common characters. And by the way, that's a code that fits nicely in 1 byte. You see, because that's actually ASCII is actually 7 bits, excuse me, but you have an extra bit left over. But that fits real nice into the 8-bit code that makes up a byte, which is a standard unit of information that processors like to handle. By the way, bits, bytes, and words are similar to each other, but just different sizes of binary numbers. So a bit is 1 single binary digit, a byte is 8 binary digits, and a word is some multiple of a byte. So it could be 16-bit word, 32-bit word, 64-bit word, something like that, or even 128 or 256. Well, let's take a break now. I'm running out of time on this video, and we'll come back and I'll talk a little bit more about this.